Today we're going to start a new lecture, to take a break from spectroscopy that we just completed. And we're going to start our new lecture on electroanalytical methods, and it's going to be largely really an introduction to it, just because electroanalytical methods are fairly vast. And so we can only cover, just a summative aspect of it. Maybe just to remind you, the scope and the history of electroanalytical methods, maybe the three fathers, I would say, of electrochemistry, comprises of, these gentlemen who developed the theoretical concepts of, Faraday, or rather of electrolysis, where he indicated, that one important law is the Faraday law of electrolysis is the amount of substance, that is deposited from an electrolyte would be proportional, to the current, that is generated if at all that chemical species is redox active. So you'll be measuring essentially charge. So essentially we can say, he's the father of, this technique, called coulometry. Now, the other gentleman that you guys know well about, is Nast, the gentleman who developed the Nast equation. And that's the basis, of, potentiometry. And you can see the importance, of some of these techniques in light of, these gentlemen actually won a Nobel Prize, so Walter Nast, won the Nobel Prize for the development of the theory of potentiometry, based on the Nast equation in 1920. So not very long ago, just 100 years ago. And then you've got, these Russian gentlemen, who developed the theoretical aspects of voltammetry, although at the time he called it, polarography, and he won a Nobel Prize, in 1959, again, to show you the importance of the technology, that he's developed in the light of, winning these awards. And you're going to see actually mainly the basis of voltammetry is polarography. And the reason they called it polarography at the time is because the working electrode, that these gentlemen used was what you refer to as a dropping mercury electrode, which has now fallen out of favor. However, you're going to see all the theoretical basis, that we borrow, for all the different types of voltammetry, they were developed, based on, these dropping mercury electrode, or using the technique called polarography. As I've said, polarography is the equivalent, of voltammetry today, which is going to be mainly the focus, really, of this chapter. Now, remember, electroanalytical chemistry, is based on the premise, of a redox equilibrium or redox process, that is taking place for a chemical species. And just to remind you, redox refers to a chemical species, that is undergoing reduction, and is undergoing possibly oxidation as well. Now, while we may say that only certain types of analytes are redox active, okay? Now, you would see actually almost all analytes out there are redox active. All analytes there, have got an electrochemical signature, which is what I'm referring to as, redox activity. The challenge is, you've got some analytes that need very high voltages, to be either oxidized or reduced. And those voltages, are too high such that it becomes, impractical sometimes, in the lab using the systems, especially the voltage, supply systems, that we have. And so you would see, most of the current, redox active compounds, are mainly those that I can reduce within around -2 volts, to about, +2 volts. But if you had, a voltage supply, out there that can do even higher than 2 volts, plus minus to 2 plus 2 volts, then you realize almost any analyte there, can actually be oxidized. Maybe from your Chem 1 or 2, you remember, this table that is called the standard reduction potential table. And you would see, most of the elements there, the cations and the anions have got very, very specific, standard reduction potentials. Meaning, if at all I get a standard reduction potential specifically of, say, 2.87, I'll realize, that is actually fluorine, that is being reduced. And that's what I'm trying to refer here, that every analyte there has got a very specific, electrochemical signature, meaning electrochemistry can be a very, very specific and selective, technique, which is very, very good. Selectivity, is such an important aspect or figure of merit out there, because of course analytes, exists in a labyrinth, of lots of chemical matrices, which is a very big problem in analytical chemistry. And so if at all you've got a technique out there that is fairly selective, then you're winning, against these matrix effects, that we struggle with when we are doing chemical analysis. And so you can see the importance really right from the get-go of analytical, electroanalytical chemistry is that it is fairly selective, because of this idea of each analyte having a very, very specific, electrochemical signature, or what I'm referring to as, they can be reduced or oxidized at very specific voltages. Now, as I said, there are many branches of an electroanalytical method, and of course we can only cover so few, but this is an important slide, for you to see the wide scope or all the different electroanalytical techniques. You've got photometry, which I'll focus a lot on. And remember the definition of photometry, very, very important. You're measuring current, that's your signal. Current is your signal. And you're measuring as a function of changing potential. So the voltage, is actually changing, and you're measuring the current as you change the potential. That is photometry. Amperometry, on the other hand, you're measuring current, that's your signal again, very similar to photometry. The only difference is, you're fixing, the potential. So in this case, you would fix the potential, meaning you should know, possibly the standard reduction potential of what you're analyzing, and then you fix it at that, and then now you measure the current. And you're going to see it's a very, very important technique, in lots of different environmental as well as medical diagnostic applications. Now, the other type of electroanalytical method is what you refer to as potentiometry, developed, by Nast in, about 100 years ago or so. You see potentiometry, you're actually measuring, remember, voltage. So in this case, the signal is actually voltage or potential difference, that's what you are measuring. And remember, there are two types of actually potentiometry. There's what you refer to as a classical potentiometry. And the classical potentiometry is where you are using your sensor as a galvanic cell. And all of us, I think, know about the galvanic cells. Now, but you can also run potentiometry, using the so-called non-classical potentiometry. And this is where you generate a potential difference, just by having, two surfaces, that are coming into contact. So this one is what you refer to as membrane potentiometry. And it's actually the most common type of potentiometry that we use currently, for different types of sensors. For example, your pH electrode. Your pH electrode really is a non-classical potentiometry, meaning you really don't have any Faradaic or redox reaction taking place. Galvanic cell, you've got a redox reaction taking place. Non-classical, you do not have a redox reaction taking place. So the potential difference is only from, you've got, say, a glass membrane. If at all you have the case of a pH electrode, and then maybe you've got hydronium ions that you are measuring in the sample. And inside the membrane, you've got a known concentration of hydronium ions, I think, which is usually around 3 molar concentration. And because of this charge separation, between the analyte solution that you're analyzing, and the inner solution that is well known, you develop, a potential difference across, the glass membrane, and that is what you measure, as a voltage. That is what you refer to as a non-classical, potentiometry, meaning you don't really have a redox process, that is taking place. Now, having said that, if you look at this paper, for example, it reveals, lots of misconceptions, on a non-Faradaic / or what I'm calling non-classical potentiometry, because most of the theory, of the non-Faradaic potentiometry came from the galvanic cell or the classical potentiometry. And because of that, you've got some assumptions, that are used with galvanic cell that are translated to non-classical potentiometry that do not quite apply because, of course, the basis of the two are very, very different. With classical galvanic cell, you've got a redox process that is taking place. With non-Faradaic, or what we are calling non-classical potentiometry, you don't really have a redox process that is taking place. You're just generating, the potential difference, from a membrane barrier, and that's how you're generating that. And of course, measuring the voltage associated, with that charge separation across a membrane. I won't talk a lot, about potentiometry because we talked a lot about it, in Chem 211. But the reason I have it here, again, is just to show you it's one of the main branch of electroanalytical techniques. Now, other branches of electroanalytical techniques, there are many, like the coulometry that I just mentioned about. And the coulometry, that is based, on the Faraday's law. Now, but you've got others, such as impedance spectroscopy. And impedance, refers to as when you are measuring the resistance as a function of frequency. Okay, so you can see it's very similar to resistance, measuring resistance. But in resistance, you don't worry, about the frequency, of the electric current, that you are producing. But in impedance, you worry about, the resistance at a specific or at a varied, frequency. So impedance, very common, type of actually electroanalytical technique out there, and we use it a lot in our lab, but it can be fairly complicated actually in terms of the theoretical basis of it. But anyway, make sure you know that it exists. It exists. Now, conductimetry, it's another method, of electroanalytical methods. And essentially, this is where you're just simply measuring the conductivity of a solution using a conductivity meter. So not very, very complicated. Okay. And you can also have capacitance, which is another method, of electroanalytical, chemistry. And capacitance is very related, to current, because you can actually measure or convert current into capacitance, just by taking the current and dividing it, by the scan rate, that gives you the capacitance. So they're quite interconvertible, with voltammetry, for example. But I guess, as I said, my focus is going to be mainly voltammetry, amperometry, and I'm going to mention potentiometry. And the reason I will, is because you're going to realize, some of the theory, of voltammetry and amperometry was actually developed, from the potentiometry as well. So very quickly, what are the advantages, of electroanalytical methods? Now, if you compare electroanalytical methods, to spectroscopy or even to chromatography, you're going to see that electroanalytical methods wins a lot in a couple of areas. One very critical area is the fact that with electroanalytical method, you can do speciation of your analyte, meaning you can determine the oxidation state, of the analyte that is present in your sample. And that is very, very important, because, for example, if you are dealing with heavy metals, for example, you're going to realize different oxidation states have got different levels of toxicity. Look at arsenic 3 compared to arsenic 5. We know arsenic 3 is a lot more toxic, compared to arsenic 5. And so in that case, if at all you are dealing with some water contamination, you would like to care, what form of arsenic, is actually present in water. Is it arsenic 3, which is more toxic, or is it arsenic 5? Remember, if in that water you just used ICP-OES that we covered in class, you would realize that you will not be able to do speciation. ICP-OES is only going to give you the total arsenic that is present. Electrochemistry, on the other hand, is going to give you, the speciation, the different oxidation states, that the analyte is present in. And it's going to give you those results very inexpensively. Electroanalytical methods are the most inexpensive techniques out there, and even better, is that, electroanalytical techniques, you can really make them really, really small into micro scale or even nano scale, meaning you can take it to the field out there. You can even wear it, these days with the wearable sensors. The basis of wearable sensors is electroanalytical techniques. So you can see the importance, of these growing field, because of the need, to miniaturize devices and take them out to the field. Now, one other important, I think, advantage, is the fact that instead of measuring just concentration, which is the case for most of the spectroscopic techniques, with electroanalytical methods, you actually measure, or you can determine the activity, of the analyte. And why is that important? Now, remember, the activity of the analyte, gives you a better reality, of the environment, of that analyte is, okay? So it's very different from concentration. So let me just remind you, the relationship between activity, and concentration is based on that relationship. That activity is proportional, to concentration, with the proportionality constant, being, the activity coefficient, the gamma, the activity coefficient. How do you determine the activity coefficient? You determine it, using this so-called de Boerhaave equation, which we talked about in Chem 1, or rather 211. And you can see, the activity coefficient is proportional, to this thing that is called ionic strength, the mu. Now, the ionic strength is very, very useful in the sense that the ionic strength, is proportional, to the charge, of the analyte. And so based on that, you can tell, the conductivity or the conductive environment, in which the analyte exists. And that is very, very important. They can give you some information, of the nature of the charge of the species, that is present. And that relates back, to the oxidation state, right? Because the charge is dependent, on the oxidation state. So again, you can see how much useful chemical information, that you can actually get, from electroanalytical techniques that is not really possible, with the spectroscopic techniques. I remember in the spectroscopic techniques, we make these assumptions, in chemical equilibria, for example, where the activity coefficient, you imagine is very, very close to 1. And that's why, we assume, that the activity coefficient is actually equals to the concentration, which is not always, the case. It's an assumption. And of course, there are many other advantages, of electroanalytical techniques. For example, assume you're doing medical diagnostics, ideally, you want to do the analysis in vivo, so you want to, insert probably the sensor. If at all you're trying to look at the brain activity, you don't want to do surgery of the brain, but instead with electroanalytical techniques, you can essentially, insert these nanoscale, electrodes, and actually do, the electroanalytical chemistry of very, environments that are otherwise difficult, to do using spectroscopy. So very quickly, let me remind you, the basics, of electrochemistry, the underlying basics, which is what we really use, to build all these different types of electroanalytical techniques. Just to remind you, there are two types of cells. And of course, whether you're dealing with voltammetry, amperometry, potentiometry, they are really electrochemical cells, okay? So there are two types of cells. You guys did this in Chem 102. You've got a galvanic cell. Now, galvanic cell is where you've got a reaction in the anode and the cathode, and those reactions are spontaneous, okay? Meaning you're generating electricity. You're generating energy, from that reaction, okay? It's a spontaneous reaction. On the other hand, you've got this other type of electrochemical cell, which is sort of the reverse, of the galvanic cell, which means that for you to do a redox reaction, you need to drive that reaction that is non-spontaneous by giving it energy. And that is what you refer to as electrolytic cells, okay? Potentiometry, is a galvanic cell. Amperometry and voltammetry are electrolytic cells, meaning you need energy with amperometry, you need energy in voltammetry, and that is why you guys in the lab, remember you had that potential start, right? And the potential start, was the one that was supplying the voltages that are needed, to drive the redox reactions, when you are doing voltammetry, okay? Now, another quick reminder, is sort of the setup, for these electrodes. Typically, in both galvanic and electrolytic cells, you need two electrodes, okay? You need two electrodes. In practice, you use three, but initially, you need two electrodes. One of the electrode, of course, is a working electrode, and the working electrode is what sometimes we refer to as the indicator electrode. Essentially, that is your sensor. The indicator electrode is a sensor. It's the one that you are putting, in the sample that you are probing. Okay, that's the indicator electrode. That one is typically your cathode. All right, and it's typically what is on your right-hand side. So as far as the Nast equation is concerned, you put that in the right-hand side. So that's your cathode. That is your working electrode. That is your sensor. On the left-hand side, on the other hand, you've got an anode. And an anode, of course, that is where reduction takes place. Reduction takes place, in the anode. And that is on the left-hand side. And in most cases, that's going to be the reference electrode. And the reference electrode has got a standard potential. So its potential, it's fixed, it's known. Such that the only thing that is changing in terms of the potential, is the right-hand side, which is the working electrode. Hopefully that's clear. And then so you're going to see, the E of the cell is going to be equals to the E, of the right-hand side minus the E of the left-hand side, which is the reference, the E of the reference. So there are many, or rather there are three types of reference electrodes, that are typically used out there. And again, as I say, the reference electrode has got a fixed potential. The most common, reference electrode, that you guys used in the lab, is a reference electrode that is made from silver, the silver chloride reference electrode, that is based on this redox process with an electrode potential, of 0.197. Now, the other type of reference electrode is a so-called saturated calomel reference electrode, which is based on mercury. And mercury, is undergoing this reduction process, to give you, the silver, the silver metal. Yeah, the silver metal. And it's got a standard reduction potential, of 0.26 or 0.241 volts. So again, fixed potential. So the other type of reference electrode, is a so-called standard hydrogen electrode, which is based on electrolysis, really, of hydrogen using platinum as a wire. And this one is arbitrarily, set at a voltage of 0. And so these, voltages that I talked about, for the silver chloride or saturated calomel electrode, they're actually based on standard hydrogen electrode, being set at 0. So this is actually the reference electrode that is used, to determine, the voltages, for these two. Of course, in practice, standard hydrogen electrode is very difficult, to make and to use. And so it's actually rarely used, in a conventional lab. So the two, sort of common reference electrodes are the silver chloride, and the standard calomel electrode. The problem with the SCE is that you're using mercury. Mercury is toxic. And for that reason, again, it's fallen out of favor because of that, leaving us with just a silver chloride, as the most common, reference electrode. Now, remember, you don't always have to buy these reference electrode. And I guess, when we are trying to train you, on the research projects about the art of innovation, where you don't have to you don't have to buy everything. You can actually create it yourself. And for us, we just make our own reference electrodes. Previously, we used to buy maybe a silver chloride, reference electrode. On the market is gonna cost you about $100. And yet in the lab, ourselves, we can make it, for less than maybe 2 cents. Because all what we do, is take a capillary. The capillaries that you use in the lab, melting point capillary, we just solder it, and then we we infuse it, I think with 3 molar of KCl, and then we insert, a silver wire that we have bleached, using regular bleach, like Clorox, to give you the silver chloride. And you've got a perfect, reference electrode doing that, which is exactly really how they make it commercially. So you can make it in the lab, yourself fairly easily. Now, before we continue to amperometry and voltammetry, let me very quickly, remind you, the importance, of potentiometric sensors, because they are still fairly common out there. And maybe the most common type of potentiometric sensor, as I mentioned, is a pH electrode. All right. And the basis of it, remember, is a glass membrane. The glass membrane is very selective, to capture hydronium ions, and because it captures hydronium ions, you can create, an ionic charge separation, between your sample, and the inner solution, that is present inside the membrane that you actually feel. You feel a glass membrane. I think with I guess it's 3 molar, HCl, and that one is a constant, concentration, and then you can determine the potential difference, across the glass membrane. But other than the pH electrode, there are so many other types of potentiometric sensors out there. For example, you can have a calcium ion selective electrode. where the membrane in this case, is just a polymer, and then you have what you refer to as an ionophore, that actually captures, calcium, or a ligand. Sometimes ionophores or ligands, that can actually selectively capture, the calcium. And again, similar, to the pH electrode, you can determine the charge separation between the inner solution, that the concentration is known, and the outer solution. Maybe another important example, of potentiometric sensor is a so-called, potassium, ion selective electrode or potentiometric sensor, which is based on an antibiotic, called valinomycin. So valinomycin, is impregnated on a plastic, on a polymer, such as that. And the valinomycin, is known to capture, things like potassium, because valinomycin is a packed molecule. It's a molecule that has got a hole. And the hole, can have the same size, as potassium. And so based on that, the valinomycin, an antibiotic actually, it captures, potassium. And again, it's a membrane, it's a plastic, it's a membrane. And so based on that, you've got charge separation, and you can determine the potassium that is present. So as you can see, really, potentiometric techniques are an equilibrium, sort of type of technique, where you have to wait, you dip the sensor, right? Even a pH electrode, you dip it inside the solution, you stir the solution, to allow enough of the ions to migrate to the membrane. They get captured, and then you actually measure, the potential difference across that membrane. Now, one thing you're going to see about potentiometry is that they tend to be fairly reproducible, by the way. And I think you guys know this, because when you dip an electrode, you always see the voltages changing, for quite some time. And you really have to wait, until it really stabilizes, because of that equilibrium process, that is getting established. And we know equilibrium process is a function of time. So the other type of electroanalytical technique that we're going to talk about, is amperometry. And as I mentioned before, amperometry, you are measuring the current as a function at a fixed voltage. You're measuring current at a fixed voltage. And amperometry really is the basis of lots of biosensors, out there. And maybe one most important, commercial biosensor, is the so-called the glucose meter, which is based, on this amperometric technique. And all of us, I think have seen it, where you just have a strip, that looks like this. And here you've got the working electrode. And the working electrode, you coat the working electrode with an enzyme that selectively oxidizes glucose to give you a redox reactive species. And because we know enzymes are very, very specific, to certain types of analytes, it becomes very, very selective. For example, a glucose sensor would be very, very selective only to glucose, while it is going to be blind, to all the other types of matrices that would be present in blood. And the reason it's very, very specific is because you've got an enzyme, that is specific to oxidizing glucose, that is causing the production of the redox analyte, that you actually measure, after applying a voltage, to measure the current. So you can see, your electrode systems, you've got the silver chloride, and then of course you've got the working electrode. And of course, for the electrical connection, you would often print a conductive ink, from the working electrode, so that you can connect it, to the alligator clip, of the potentiostat. Again, you can see, you've got a potentiostat, which is a battery, because you're dealing with an electrolytic cell. So you need to drive energy to cause the redox reaction of the redox species, that is actually generated. So very quickly, in terms of the chemistry, so if at all you've got glucose, and then you impregnate the working electrode, with an enzyme, such as glucose oxidase. Glucose oxidase oxidizes glucose into glucolactone and hydrogen peroxide. Now, hydrogen peroxide is a very redox active species, which you can easily oxidize, to give you oxygen, plus 2 electrons, which you are measuring, as a current at a fixed voltage. I think typically, the voltage that most people use is around, I think, 0.4 volts, although that can change anyway. But anyway, that's a voltage that you typically use, okay? Now, and so based on that, you can actually determine, your glucose very selectively. And that's exactly, how the glucose actually sensor, really works. Now, lately, people have started to improve the electron transfer, of the solution, of the analyte in the solution, to the working electrode. Because remember, you've got the working electrode, and then you've got the sample inside the working electrode. And whatever is happening is, you are driving the voltage on these electrodes to cause the oxidation, of the analyte, in solution, or even the reduction, of the analyte in solution, depending on the polarity, of the electrode that you are using. And so you need to, and of course you're measuring, the current, that is actually generated. Now, to improve the electron transfer between the solution, to the electrode, other than using the electrolyte, sometimes people coat the electrodes, with what you call a redox mediator, that is very, very good in electron transfer. And the redox mediator, typically is a material, that is rich in electron density. And one of such, material is what you refer to as the ferricenium. And ferricenium, as you can see, is an organometallic, type of molecule that has got an ion center. And it's connected, to two aromatic rings, meaning they are fairly rich, in electron density. And because of that, you're able to get very good electron transfer. It's really a mediator, from your sample. You get the electrons, and then you've got, this mediator, that is taking the electrons and shuttling those electrons, to the electrode, so that you can actually measure the current that is generated. So essentially, these are called shuttling, shuttling molecules, that carry the electrons, to the electrode. And they're very common these days in terms of improving the sensitivity, of the glucose sensors. Now, based on that premise, actually my group, we've worked and published quite a few papers, on different amperometric biosensors, based on exactly the same concept of hydrogen peroxide generation being a very redox active species. But in this case, you're using a different type of enzyme. I'll give you a quick example. If at all you're interested in detecting, say, cholesterol, very common problem out there in blood, you can just simply use exactly the same device as a glucose sensor. The only thing is you change is the enzyme and use, say, cholesterol oxidase. And cholesterol oxidase oxidizes cholesterol selectively to give you hydrogen peroxide. And with hydrogen peroxide, again, you can very quickly, detect it using amperometry. Now, other than, cholesterol, you can even detect, things like, say, lactate. And lactate, again, if you use the right type of enzyme, such as lactate oxidase, and lactate oxidase is gonna give you hydrogen peroxide, as a product. So again, you can determine, lactate concentration, say in sweat. Maybe another thing that you can do, is something like fat, in sweat, like the triglyceride. I think all of us, always like to have low triglyceride, amount in our blood. And you can use something like the triglyceride oxidase, to give you again hydrogen peroxide, as a product, that you can do. You can oxidize, to give you a current. So again, you can see you can actually create or innovate using very similar concepts, that are known, and create fairly new devices. So in the next lecture, we're gonna talk very briefly about the aspects of photometry which are based on really amperometry. The only difference with photometry, as I said, instead of a fixed potential, in this case you're sweeping, or you're changing the potential. You're changing the potential, but you're exactly measuring the current as you change the potential. That's what we're going to talk about, in the next lecture.